Assalamualaikum warahmatullahi wabarakatuh. My name is Naina Batrisha binti Batia. I will talk about our problem statement. Now, let's look at our problem statement. Our project is divided into two main challenges. First is modeling. We are investigating how to accurately represent the physical expansion of a piston rod during repeated heating cycles. To do this, we are comparing two mathematical approaches. First, an arithmetic sequence, which assumes a steady increase, and a geometric sequence, which assumes a compounding growth. Second is the safety threshold. In engineering, precision is life. We need to calculate the exact point, either the number of cycles or the specific length, where the road becomes unsafe. Our goal is to predict failure before it happens to prevent total engine destruction. Next, I will talk about Pbl table. To organize our findings and strategy, we utilize a Pbl table which stands for facts, ideas, learning issues, and action plans. First, for the facts, we have established our starting parameters. The initial length is A1, which is 101.0mm, and the engine's maximum safety limit, which is M, is 112.5mm. For our models, we are using a constant increase D of 0.7 for the arithmetic sequence and a growth ratio R of 1.007 for the geometric sequence. Moving to ideas, we recognize that the road expands due to heat fatigue over time. We are testing two theories, one where growth is linear, which is arithmetic, and another where is compounds by ratio, which is geometric. We know that if the road exceeds M, the engine will fail. Next is learning issues. Under learning issues, we identified what we needed to solve. Specifically, we needed to identify the correct formulas for the n minus th term, which is Tn. To find exactly where the road reaches or exceeds the 112.5mm limit, we also question which model poses a higher risk to engine safety. Lastly, our action plan involves reviewing our Form 5 textbooks for sequence formula and using tools like Microsoft Excel to generate comparison graphs. This allows us to visualize the data and verify our manual calculation effectively. That's all from me.
So, hi everybody, my name is Nursuliniti Muhammad Ridwan and my number metric is 88251364. So today I would like to introduce my part of this slide. So as you can see, this is a result and manual calculation that I did in manual and Excel. So this is the box plot result I used to prove our data is the same as the calculation from Excel and manually. To solve the arithmetic part, I used the arithmetic formula, which is extension equals AR to the n power minus 1. To find the sum in arithmetic is n divided by 2 in parentheses or plus parentheses n minus 1 times d. For average, both sequence use as n division and to find the geometry as the extension, I use the formula n equal AR to the n power minus 1. To find the geometric sum, I use as n equal times in brackets 1 minus r to the n power divided by r minus 1. So this is the result when I use calculation, when I use manual calculation. On this slide, it shows results of arithmetic sequence in Excel. There is essential, which is n, maximum safe limit in m, constant increase is d, which is different 0.7 mm, and growth ratio r. Growth ratio it doesn't have in in arithmetic sequence, it had an geometric sequence. So with several functions in Excel, let me sum to find the first try a sum and scatter to make a graph. The example graph from our group, which is Tn versus n, Tn in x-axis and n in y-axis, and same thing in xn versus n. So both of these are examples from our group. And from geometric sequence, it has R growth ratio, which is 1.007 mm. And geometric sequence, it has the same thing as previous page before this. And the last one is part C, which is comparison between arithmetic and geometric sequence graph. It's shown a compare between two sequence graph that I took cycle geometry versus max safe limit for the green line one. And for the red line one, I use extension versus n geometric sequence. And the blue line one, I use the extension versus n arithmetic. That's all from me.
Assalamualaikum and very good evening. My name is Nur Umairah binti Airul and my metric number is AA251052. So today I'll be presenting about my part, which is discussion part. So let me get straight to the point. So which model predicts unsafe conditions earlier? The geometric model actually predicts the root will break first on the cycle 17. Meanwhile, the arithmetic model predicts it will break on cycle 18, which exceeds the maximum safe length, which is 112.5 millimeter. So in this case, the geometric model predicts the unsafe length limit much faster. And then which model shows faster growth? Actually the geometric model also grows faster overall. It is because the arithmetic model's growth is a straight line on a graph, but the geometric model curves sharply upwards, showing a much quicker increase in root length as the engine cycles continue. And next, what are the effects of heat on the material? Repeated heating makes the root expand a little bit more with each cycle. So the arithmetic model suggests that the root expands by the same small amount every time it gets hot. Then the next one, as for the geometric model, it shows that the heat damages the material over time, making it expand even faster with each new heat cycle. So in this case, the geometric model is actually it's actually unsafe because it expands even faster with each new heat cycle. Okay, so what are the factors influencing the results? So there are three factors that influencing the result. The first one is material properties. The expansion depends on the material used. So in our case, in our model, we assume the coefficient of thermal expansion is constant. But in reality, it can change with temperature, so the actual expansion may be slightly different. For temperature variation, the model assumes the temperature increases consistently. However, in real situation, the temperature can fluctuate, which affects how much the piston rod expands. And lastly, for measuring mistakes, small errors can happen due to instrument limitations or human error, and this can slightly affect the final results. So that's all for my part. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Fadin Afia Binti Suhaimi with metric numbers AA251649. So today I'm going to presenting about my part in this slide, which is conclusion. So to conclude our case study regarding the piston rod thermal expansion, we can see that we can show that the piston rod length increasing differently depending on the mathematical model. As proven in the graph below, from the arithmetic sequence, we can see the graph of arithmetic sequence with blue line is increasing steadily and reaches the maximum safe length at cycle 18, while the geometric sequence with brown line or orange line, we can see that the graph show the length of piston rod expand faster and proportional, reaching the limit earlier at cycle 17. Actually, a geometric sequence graph should be a curve. However, due to very small changes in their growth ratio, so it almost similar as straight line. So overall, temperature directly affect rod length, and different models predict different behaviors under the same condition, which mean even though both arithmetic and geometric sequence calculation was held, the piston rod is heated repeatedly in the same condition. However, the result still have a little different. Beyond just predicting numbers, both of the arithmetic and geometric sequence give us a very practical insight. As example, as we do calculation before, we did a calculation that very helpful for us to predicting the cycles number and when the rod length will reach its maximum limit. So after we make the calculation, we make a graph. The graph is very helpful for us to see the trends and also comparing both of the model. So we can see the combination of mathematical and science is very helpful, especially for engineers, scientists, and those who work in the related field, which mean they can predict, they can plan for the safety caution and then plan for the material structures and also optimizing the design. So lastly, we can see that mathematical model is not just theoretical but also practically useful for solving a real life situation. That's all from me. Thank you.
On this page, as you can see, this is an example of a basis being based on arithmetic sequence and geometric sequence that helps our group create this assignment. So that's all from me. Bye.